Welcome to today's webinar, a new real fluid modeling framework applied to cavitation simulation, brought to you by CONVERGE Science. Thank you for joining us today for the 17th installment of the 2024 CONVERGE webinar series. My name is Matthias Sulis and I am part of the business development team at CONVERGE Science. I will be your host for today's event. I'm glad I can be here with you today and hear from our partner at IFP Energies about real fluid modeling with CONVERGE. CONVERGE Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speakers for today's event, Dr. Chaouki Habchi. Dr. Habchi received his PhD in the field of computational fluid dynamics from the Paris-Sorbonne University in 1990. In recognition of his achievement, particularly in the two-phase flow modeling, he received a Management of Research HDR degree in 2006 from the National Polytechnic Institute of Toulouse. Dr. Habchi currently leads the two-phase flow modeling group in the Digital Science and Technology Division at IFP Energies Nouvelles. He has also been a member of the Scientific Committee of ILAS Europe for more than 10 years. Without any further delay, I will now pass the ball to today's speaker. Thank you all.
Hello everybody, my name is Chaouki Habchi. Welcome to this CONVERGE webinar. In this webinar, I will introduce a new real fluid modeling framework applied to cavitation simulation. After the introduction of the objectives, the real fluid modeling computational methodology will be detailed, and then some results of this new framework in the aim of validation is discussed before the conclusion. We have two main general objectives. The first one is to develop a predictive and efficient CFD model for multi-component two-phase flow simulation in the context of renewable fuels under different thermodynamic regimes such as subcritical, supercritical, and transcritical. The second objective is the investigation of the different physical processes during the fuel injection event, such as in-nozzle cavitation, liquid atomization, phase change, and mixing. So to achieve the objective of building a unique model for the three regimes, subcritical, transcritical, and supercritical, we need to tackle different objectives. The first one and the most important is the transition between the different regime and the transition between the atomization and diffusive mixing. This is here discussed using the image from the famous paper of Chaouki using liquid nitrogen injected in gaseous nitrogen. In the left side, we have a TP diagram which show the saturation line and the Widom line. So in the first regime, in the blue one, at subcritical condition, when the pressure, reduced pressure is less than 1, we go from liquid to gas, and we go through the saturation line, which indicate that phase change is happening, and also that the surface tension is significant, and then it's allow the formation of droplet at the liquid core when the liquid is injected, as is shown in the image, the first image. The second regime go from liquid-like and gas-like and go through the pseudo-Bowling line, which is the Widom line in the dotted line and the TP diagram. This is the location where the CP is maximum, for example. And this maximum of CP may decrease when the pressure is increased. As in the third regime, where no longer droplet is observed, and we are going to a regime where the liquid-like is transformed in the vicinity of the Widom line in a gas-like state, and the flow is becoming very, very diffused. So this indicates that a challenge is this challenge is important to be tackled if we want to be able to compute the injection from supercritical to subcritical condition. So the second challenge is to be able to compute thermodynamic and transport property which are non-linear, that exist in the case, for example, of the transcritical system. So we need to use, this justifies the need to use real fluid equation of state as shown in the right-hand side figure showing the specific heat CP as function of the temperature. In this case, we have a peak and a nonlinearity that is obvious at near 130 K. In the case of a multi-species system, the condition become much harder, as the limit between the sub and supercritical depends on the critical point of the mixture, which is a function of the mixture composition. As we can see on the right-hand side in the figure, when changing the percentage of nitrogen in the dodecane, the phase envelope in the TP diagram changes, and the critical point of the mixture change location. Another challenge is the simulation of in-nozzle cavitation effect on the spray. As shown in the experimental work of Su, there is a significant coupling of the internal flow and the external liquid jet atomization. Therefore, we need to be able to compute such coupling of the in-nozzle flow and cavitation. This will be among the results that we will show in the next slides. Last but not least are the numerical challenges of coupling of real fluid thermodynamics and CFD. Let's now see the computational methodology that have been used to achieve the real fluid modeling framework. The computational methodology is based on the governing equation of Navier-Stokes. These equations are applied on the liquid or the gas or the two-phase states. So this model is a fully compressible two-phase flow model under mechanical and thermal equilibrium assumption with a diffused interface. This means that the two phases have a single velocity, pressure, and temperature. The system of equation is closed thermodynamically using real fluid equation of state. Most precisely, we are using a tabulated equation of state, and the table is generated by the IFP Carnot library. So to be able to compute all the outputs that are listed in the right side, we need to give as inputs the temperature, the pressure, and the composition of the species. These inputs are given to a VLE solver, which is typically a TPn-Flash and isothermal isobaric flash, using a real fluid equation of state that could be the Payne-Robinson, for example, cubic plus association for oxygenated fuel, for example, or SRK. We can also use volume translation inside Carnot to correct properties that may not be enough accurate. So in summary, the RFM model is a homogeneous two-phase mixture model plus a thermodynamic table generated by a VLE solver using a real fluid equation of state, and all this give the real fluid model with the assumptions that the two phases are in local mechanical and thermal equilibrium and thermodynamic equilibrium. Before going to discuss some results, you should note an important feature of the RFM modeling framework is that the interface is not tracked. In fact, this characteristics makes the code very simple and very efficient and robust. Why there is no interface tracking? It's because when we are in the solver, at each time step and each cell, the table, and the thermodynamics inside the table will tell you in which state you are, if you are in liquid, gas, or two-phase. And if you are in two-phase, it tells you also what's the volume fraction of liquid and also the composition of the liquid and the gas. So this is a powerful method that allow the computation of dissolved gas inside the liquid as well. It's well known that for the cavitation, for example, the dissolved gas will make the cavitation easier to happen. And the nucleation in general is promoted by dissolved gas. So the capability of this thermodynamics method to track the interface and the two-phase regions is really the most important feature of such modeling. So if you are interested in more details about the RFM framework and modeling methodology, you can go to the reference listed below there, and you will find much more validation of the model in different cases. Here I will discuss only one computation of fuel injection modeling related to the ammonia fuel injection. The main characteristics of the case setup are given here. First of all, we have in the right side the injector that we have used. It's a 1/6 injector. In fact, we can see the hole in red going to a cylinder that has 10 millimeter diameter and 30 millimeter length. The diameter of the hole is 319 micron. It's a straight one, k equals 0, and the needle is fixed at 481 micron. So the setup consider a base size grid of 400 micron, and the minimum size are 625 micron near the wall embedding, except wall chamber. The solver is of course CONVERGE CFD solver with RFM, and the turbulence modeling used here is Urans K epsilon energy. The PV pressure velocity coupling is carried out using a modified real fluid piezo, and the time step is between 10 to 0.6 nanosecond, with the CFL equal to 0.2. So there is also the initial and boundary condition, as we talked about the dissolved gas in the liquid in the ammonia. Here is taken very small but significant 5 10 minus 4, which correspond to the dissolved gas at in the reservoir of a car, for example, at 1 bar. So the temperature, initial temperature is 300, the pressure 15 bar, and the injection pressure is 120 bar. Next, we have also the thermodynamic table, which is generated using the ammonia N2 system with 131 point in the temperature axis. We use log 10 for the pressure between 5,000 Pascal and 200 bar. And for the concentration, we have used 2001 pound. So this table has a size of around 10 gigabytes. We can see here the results of the vapor fraction. What's obvious is the cavitation that appear on the upper side of the hole near the entrance from the sac. As usual, this is classical, and we can see that the cavitation is deviated to the other side due to the flow inside the hole, and is affecting the velocity, the injection velocity. Here is presented the velocity, and if we focus our attention on the exit, we can see that the profile is not flat, and this proves that the cavitation is affecting the jet, and that the computation of the in-nozzle flow is necessary in this case to compute the injection and the right mixing. Next, this movie is showing the temperature flow field in this plane, and it shows mainly the high cooling effect at the spray boundaries, where the evaporation of ammonia is happening. So this is expected from this kind of fuel because of its high latent heat of vaporization. Finally, the conclusions. The real fluid model developed recently in CONVERGE has proved to be very versatile, as it is able to simulate and investigate the injection and mixing of almost any fuel. Also, the RFM model does not include any fitting coefficient for the cavitation modeling, for example. The proposed RFM model is shown to be capable of dealing with cavitation and its effect on the spray using a single simulation. Finally, I have to acknowledge that part of the work has received funding from the European Union Horizon 2020 Research and Innovative Program in the framework of the EDM project. Thank you for listening.